And all right, good. I think we're good here. Okay, chapter 6. All right, one thing we've got to cover, something called confidence intervals. And one kind of the way we do statistics here. So now we've kind of got out of the probability stuff. Chapter 5 was almost like a little bit of a bridge, though. It talked about the normal distribution and the probability there. And so now we have this whole concept of how much confidence do you have in the data, or the amount of data that you have to represent the population. That's kind of what we're looking at. And we're entering into something called inferential statistics. We kind of have we have sample data. So this is going to be sample data, and we're trying to determine how much we know of the population, because that's what inferential statistics is all about. We're good. Got this data. I think this much of the population itself. And so, and then in chapter 7, here's where we finally start something called hypothesis testing. So we're going to test something, and then we're going to extrapolate that information based upon or into the population. And so we have chapter 7 is hypothesis testing, giving one sample. We spend a chapter doing it. And then we have hypothesis testing having 2 samples. And we spend another chapter doing that. And then we'll go on to chapter 9 and 10 from there. Okay, so let's go with it. So first things first. And the rest of the chapters here in the book, it's interesting. We're going to have different formulas, but it's based upon what you know and what you don't know. We're good. So it's really, in a sense, it's really easy in the fact that I know this, I don't know this, this is the formula. I know this, I don't know this, that's the formula. So confidence interval 6.1, when you actually know, we're trying to find the mean. And this little symbol right here just means what is that anyways? Anybody know? Standard deviation, that's it. We're trying to figure out the confidence interval for a mean. When I do know the standard deviation, trying to figure out the confidence interval for the mean when I don't know the standard deviation. There's a difference between those guys. All right, then we're going to look at proportions, population proportions. And then instead of looking at the mean, we're going to look at variance and standard deviation. We're good? That's it. So again, each section has a little formula. We do that in order to figure out what we want to know based upon what we're trying to figure out. Okay, so let's go with it here. So 6.1, if you're writing down the notes, confidence intervals for the mean, if we know the standard deviation already. Okay, of course, some definitions. New chapter, we're going to figure out some definitions here. So first things first, let me skip this one, go to this one. It's called the point estimate. I'll just draw it out. And of course, these slides, we always begin with a lot of writing because there's a lot of definitions to be had. So a point estimate, it's called the single value estimate for a population parameter. It's the most unbiased point estimate of the population for mu, or the mean of the population. And what we normally use is X bar, which is the average for all your sample set. All right, as you're writing it down, I'm going to just pause the video just for a second here. All right. So here it is. So we are trying to figure out an estimate for the average of the population. And so a single point estimate, which means like what number can I use that actually will kind of give me some information about the population. Okay. And this is the beginning part of it here, but I'm going to use the average. We're good. And so it's kind of like, what's the average age of students in the statistics class? Okay, I'm just going to get the mean of the class, right? Or I'm trying to figure out what's like, question is even more like, what's the GPA of West Coast College students? What, like one number that will kind of give me at least some kind of information? Okay, it's going to be the average. At least the average gives me some kind of information. We're good? That's kind of what we're doing here. Okay, next is 2 more things we're going to think about. Is this one right here? Oh, sorry, let's do an example here. Don't need to write things down. Let's do an example here. So research is collecting data about a college athletic conference and its student athletes. We got a random sample of 40 student athletes are selected. The number of hours spent on required athletic activities for the week are recorded right there. Find a point estimate for the population mean. So we're trying to figure out a number that will help us to understand the average. So the mean number of hours spent on required athletic activities by all the student athletes recorded here, all 40 of them, is right there. And what do? We just do this here. We take X bar, so that's called X bar. We're going to add up all the X values that we have, or the sample values we have. We're going to divide it by 40, and we got 21.1. Do we know something? We're trying to give an estimate for all of the student athletes in all the sports in all of the United States. That's what we're trying to do. But what we did is we just got a group of 40. We figured out at least their average, and their average is 21.1. So at least we have some kind of something to at least find out. That's what we're getting to. So the point estimate for the mean number of hours spent on required athletic activities by all student athletes in the conference is 21.1 hours. Okay, we're good there. At least we got something. Okay. Is it going to be the same all the time? No, right? Change to different colleges, different conference, different event, right? Different sport, right? So we kind of have a lot of fuzziness there, right? So now the question is this, though. How much confidence do I have in that 21.1 being actually the average for the whole entire population, right? That's what I want. So we're going to have two more definitions here real quick. Two more, something called the interval estimate. Now this one is a little different. This one talks about, hey, I'm going to give an interval range. So from here to here. So instead of a single point. And I'm going to try to estimate the average population parameter. And then that will take us on a whole new little road over here that we're going to talk about. And this is what 6.1 is all about. Okay, we're good. So here it is. So I'm going to say, hey, the average is kind of like between here and here. That's kind of what I want to get to. All right. And then we kind of have to think about this here. We have to think about the fact that there should be some air in as well, right? Because sample always has air inside it. So we'll put that on the back burner for now. The question really we have is this: how much confidence do we have in that range being encompassing of all the students? That's what I want to know. So another definition, guys, one more. This one in the next slide, and I think we're good, and then we'll get some examples. So the level of confidence C is this. It's the probability that the interval estimate contains the population parameter, assuming the estimation process is repeated for a large number of times. So yeah, gobbledygook here, but really what it means is this. If you have a whole bunch of numbers, if we say estimated a lot of student athletes, we say, look, it's kind of about 21.1. That's a pretty good average. So now the question is, what's the probability if I took a whole bunch of different averages of all the different samples? How much confidence do I have is that average being inside the real estimate? We're good there. See if he wants to finish up. Okay, one more thing we've got to put together in our minds, and then we'll start with some examples here. Next and last one here, something called critical values. Let's talk about this one here. So critical values are values that separate sample statistics that are probable from sample statistics that are improbable or very unusual. Cool. Okay, so what we do here, let's wait a little bit here, is we get to pick how much confidence we have in what we've picked. So in statistics, we normally go with the 90% confidence because that pretty much says, look, I got most of the data, right? Just I'm missing like 10% on each side. That's kind of what I'm looking at. Sometimes it's 90%, sometimes it's 95. And if I really want to get super critical, then it's 99%. That means I do want all the data. So let's talk about this right here. So what I want to do is I want to get a average, let's say it was 21.1, but I'm going to convert it to z-score. So z-score is going to be my middle ground. We good? Oh, you guys remember that chart, right? If I'm one standard deviation away, how much data do I have inside that one standard deviation? 68% of the data, right? In one standard deviation. Okay, I'm going to go with it. If I got 2 standard deviations away, how much data do I have? 95-ish, right? Yeah. And then if you have 3 standard deviations away, we're at 99.7, right? We have almost everything. So with confidence intervals, we like 90% is a good judge, 95 is a good judge, or 99 if we want to be super critical. So what we want to do is we want to figure out what z-score will give me 90% confidence on both sides. We're good? That's kind of what I'm looking for. And so we kind of do this little thing right here. We say, look, if I want 90% confidence, my c-values is that. I'm going to subtract it from 100 because that gives me 10. But then it's on both sides. We good? So that means I'm looking for cutting it in half. So I'm looking for 5% here and 5% here. That's what I want right there. So now the question is, which z-score corresponds to that? And so if we look at a table, or if we do the chart, the chart, we'll find that this is what we want right here. It's negative 1.645. So notice also that it's 3 decimal place accuracy as opposed to 2, because we want to be very, very specific with that one. We're good. Let's try this on a calculator. How about that? Let me jump to the calculator process here. All right, just to give you guys some confidence, ready? Just to make sure that's the answer, right? We've been doing this in the calculator so far, not by table. So let's do this backwards on the calculator. So to find the z-score, we got to go inverse of the normal distribution. So go click on second function distribution. That's cool. Go down to number 3. which is the inverse of the normal distribution. This takes us from probability back to z-score. That's what we want. So clicking on that. And so we have to shed out 5% on the left-hand side. So 0.05 is what we don't want to include. Or we actually include it. Actually, no, we're including it in our probability, right? What gives us 5% probability. All right, my average is 0, my mu is 0, and I'm going with the standard deviation of 1. That's what I'm looking for. Close that off and click enter, and voila. We get ourselves, let me move this around. There it is, my negative 1.645, there it is. Okay, you guys, go for it. Can you guys give me the positive 1.64483? Think about what you got to do here. Give you guys a few seconds to sort of think about it. So if I'm missing 0.05, right? I want to include everything but the 0.05. So think about how much I want out of there. All right, I'm going to try it as well here. So distribution, inverse. And so you talk to me here. What would be the thing that you put in here now? Say again. I go with 0. Yep, 0.95, right? We're just missing that little 0.05. We're just missing the far right tail. There's that one. To 0 is the mu, 1 is the standard deviation, and voila, are we good there? We got ourselves what we want. So for 90% confidence, we're going to use a z-score of negative 1.645 or a positive 1.645. And that gets us the confidence in the middle, right? From the average going both directions. Okay, makes sense to you guys. We're good. Okay, so this is what it is. 90% confidence interval means we go here, we take 90, we cut it in half from the 10, so 5% in each side, and we just did it by calculator, but it gives us z-scores of 1.645 or a negative 1.645. Are we good? Okay, can you give me confidence intervals? We should do this one here. 95% confidence, we're good? Ooh, this is fun. And then we're gonna do 99% confidence interval, we're good? So all yours for that. In fact, let's see. All right, I kind of separated the classroom into 2 groups here, thinking how to do this here. Let's think about it first. And so I have this piece happening, is that right? I have a normal curve on my hands, goes like this. I'm trying to find the z-score that corresponds to it. So in the middle, z is equal to 0. And what I want is I want 95% confidence. So from, oh. So I want like here to here. I want this piece right here to represent 95% of my data. Okay, good there. Left side of the class, what is leftovers on each side? Say again. Oh, okay, on both sides it's 5%, right? On each side is going to be 2.5%, is that right? So let's see. That's so I want 2.5% here, and over here 2.5%. Now let's convert that to a decimal here. So that's going to be 0.025 here. And how about a 0.025 there? Are we good? Okay, now let's grab our calculator. Let's see what we get to here. Oh, I have two. That's so cool. Okay, just need one. Okay, boom, boom. Let's gather this here. So inverse operation of my normal distribution, and I'm looking for just the 0.025. Are we agreed there? We're going from mu of 0, standard deviation of 1, voila, and the answer is? Awesome. Yeah, look at this, guys. It's negative 1.95, sorry, yeah, 9599. So if I'm going to go out 3 decimal places, it's going to go to here. But that 9 is still going to change into a 0 afterwards, right? So if I want to find 95% of my data, I don't need to put it. Sometimes statistics books, they put a 0 after the 6, some don't. Yours doesn't. So not to confuse you. You know the other side is going to be exactly mirror image, right? So for 95% confidence, we're going to use a z-scores of 1.96. We're good? Cool. All right. The 99% group, what did you guys find? What's the z-score that corresponds to 99% of the data? So let me draw it out first here. Here it is. Z-score of 0 is in the middle. All right, my desire is to have 99% of the data included right into here. This is 99% of the data right here. All right, what's left over? Just 1%, huh? Split up among 2 groups. So that means I need, hold on, 1%, is that right? Split up, so I need 0.5% here. And 0.5% here. So converting that back into decimals, right? Because we need to move once, twice for that. It gives us 0.005. Is that true? Agreed with that? Right side of the room? Cool. 0.005. I'm looking for that guy on my calculator. Anybody got it? Just out of curiosity. Cool. Okay. Awesome. So inverse of the normal curve. I need a 0.005 from a mu of 0 and a standard deviation of 1. And voila. Perfect. And so let me see how much your book does. Okay, so your book in this case, it is going to keep all 3. So negative 2.57, and we're going to go with that's interesting. Okay. Your book says negative 2.575. They don't round that one up for some reason. And I'm looking here. I have to check into that. That's why that is true. So the book uses negative 2.575 as the estimates for 99% confidence. We're good there. Okay, that's what we're going to use with what we have. Okay, one more thing before we start. 2 more things here before we start doing studies. We've got to talk about sampling error. What does that mean? Now, whenever we get a sample from a population, we always think about this whole concept of most likely we have a little bit of sampling error from just the people that we took. So, and the more complicated it gets, the more sampling error there is. So let's say we said, hey, let's figure out how much student athletes work in their sport. And when you sampled on your data, you had a lot more football players in the sample than you had tennis players. We're good? At that point, you're thinking like, okay, hold on, maybe that sample was actually a little bit too football heavy. how do I adjust for all the sports, So then what do? Do you get each of the sports equally participating in the survey, right? Then that's the next question. Then think about, okay, is it just per college? Am I trying to get all the people in California? I'm gonna have to sample some schools, right? Now I'm thinking, okay, I can't ask every single athlete. So I'm gonna sample some schools, maybe Division I schools, Division II, Division III schools, right? So because I want to see if there's a difference there, right? So now you get into sampling issues here. But yes, we always think about what's my sample error in this? Okay, some formulas here. So sampling error is the difference. It's x bar minus mu. There's your sampling error. Okay, so the question is, what tends to happen is that the average in the population, you don't know that, right? You don't know all the student athletes in all the United States, how much they spend on average in their sport. Eesh, that would be tough. But I could probably gather all the student athletes in West Hills College. I can sample that. That would be easy. And then if I take another college, take Fresno City College, and I gather the data there, right? Their average might be a little bit different than West Hills College average. We're good. So then I understand each time I take a sample, the sample might be different from sample to sample, or the average might be. So again, stuff I have to keep in my head as I do this stuff. Okay, so because of it, we have, of course, a little variable that we tabulate each time. All right, good. All right, got a few people still copying. Go for it. All right, well, let's jam. So, of course, here is our little computation for that piece here. It is called the margin of error. So how much error do you have? What's the margin of error for your for your data? Okay, this is sometimes called the maximum error of estimate or error tolerance. You'll find that as well. The greatest possible distance between the point estimate and the value of the parameter. So it is given by E. And it's pretty much the Z-score for whichever confidence you want, multiplied by the standard deviation, divided by the square root of n. Let's see, next year, since there'll be elections, you guys will see that. They say the projected winner of this election, or the poll has been taken, and this person is 53 to 47%. And says margin of error is 5%. Okay, so what needs to happen in order for us to use this sample error method is, first of all, the sample does have to be random. It can't be biased in our sample or else it's not going to work well. Second of all has to be a normal distribution. If we say it's a normal distribution, we could have only 25 people, say a statistics class, right? Or we just have to have n greater than or equal to 30, and that at least gets us a normal distribution if we start looking at average of means. All right, so notice what we need here. We need the z-score of which confidence we need. We also need a standard deviation. Standard deviation might be hard to find. We do need the standard deviation of the population itself. And then we need n, or how many values we got as the sample. So obviously, if you sample 3 people, that's probably not going to be reflective of a whole entire population. Yes, 3. Athletes, right? 3 at West Hills College and say, hey, how much do you spend time? And you extrapolate that on all of the athletes in California. Not going to be good. Okay, we're good there. Here's a formula. Hopefully you wrote it down. It is margin of error. And so now it does say this here. It does that standard deviation is known, right? So this is the formula. What standard deviation being known? Okay, so let's go back real quick here. So using that data sample from our student athletes, what we're going to do is we're going to try to find a 95% confidence level to find the margin of error for the sample mean of 21.1 hours, because we know that from the previous sample. Okay, we're going to assume something. We're going to assume that the population standard deviation is 2.3 hours. That's so 1 standard deviation equals 2.3 hours away from the mean. So let's just practice using the formula itself. Let me give you the graphic of it first, and then we'll go with it here. So the graphic of it is this right here. So because standard deviation is known, it's 2.3. Sample is random, yes. And it fits the criteria that n is equal to 40, because we did have 40 student athletes, right? We'll fill out the survey. That's get it greater than 30. So then the formula is good. Okay, so what are we trying to find? We're trying to find something that looks like this. The z-score that corresponds to 95%, we already calculated it. It's a negative 1.96 and a positive 1.96, right? That gives us 95% confidence throughout the value itself. That's cool. There's the graphic for it. So now let's actually go to the computation part. All yours there. So see if you guys can replicate what is on the screen here. So 1.96 is the z-score. 2.3 is the standard deviation. And then we take the square root of our number of athletes we surveyed. So punch it into calculator, see if you guys can get a 0.7 as well. Cool, try that, see if you guys find it. Cool, okay, done with that here. Let's see, next thing to do is now we're gonna actually make the interval. So make the interval how much, since we have a 95% confidence interval, means we have a gap of 0.7 hours each direction. That's what we have. So one more, or another definition, the C confidence interval for the population looks like that. Much easier. The formula is crazy, but what we do is we take the average and we subtract E from it. We take the average, we add E to it, and then that's going to be our confidence interval. We'll get there. Not bad. the formula looks way more difficult than it actually is. We'll see how that is pretty simple. And so that E formula right there, that's what we've written down before, right? We already have that formula. But it's this whole concept of what we do is to find the average for the population. We take our average for our sample. We subtract our margin of error to do the left endpoint. We add it in order to get to a right endpoint, and we got ourselves our interval. So let's jam with it. Let's try it here, because I think the formula is more difficult than actually the numbers are themselves. And so let's use for example 1, we're going to construct a 95% confidence interval for the mean number of hours spent on athletic activities by student athletes in the conference. So here it is. Remember, the average was 21.1 for our sample. We got an average or a margin of error of 0.7. So all we do is we just subtract these guys. So 21.7 minus is 0.7. Gets us 20.4. Are we good there? So if you want to write it down, just so you guys have it, go for it. Just kind of left endpoint. So maybe not all the stuff on the slide, but just this stuff right over here with the left endpoint and the right endpoint. And then bring it down to this right over here. And do you guys remember doing compound inequalities in algebra? Do you guys remember doing those? Like with the left-hand symbol, less than and less than. Means your lower bound is on the left, your upper bound is on the right. So you guys a little time to write that down, and we'll just do one example from beginning to end. All right, class, let's go with it here. So we just found out that 20.4 is the low end, right? And this is for 95%, right? So we're assuming that if we were to take any other samples, 95% of the time, the average would be inside this little range. Okay, and then what we normally do is we make a little graph like this. It's an interval notation. We put a little dot at 21.1. Just make a, you can go up by ones if you like. This one went up by half or went down by half just because that. You can go by tenths, just kind of however you want to have it here. But this is actually going up by a quarter each time, by a fourth. So a number line that maybe goes from 20 to 22. Find your 21 over here. So then 21.1 is just gonna be a little bit above that. Put a little dot there at 21.1 and make sure the dot actually is on the line itself, not the dot. There's no dot above the line. We're actually on the line itself. And then we're going to have these guys here. We're going to have parentheses that start at the bottom, parentheses that end at the top. And then this is kind of like just slightly shaded in. Do you guys remember doing that in algebra? Yeah, that's the one that we've done. Look at that. Now it's the application of it is now in statistics. All right, so the question is, what are we trying to say by this? What's the whole purpose here? So we're trying to say we could state with 95% confidence that the population average, right, all the student athletes, it's called in the conference, right? So assuming it's a certain sport, right? In a certain sport, the average will fall in this interval. And I can state that with 95% confidence. that's going to happen. True. Okay. All right, so here's kind of just the way they say it here. With 95%, you can say that the population mean number of hours spent on required activities is between 20.4 and 21.8. Same thing, but you want to give the verbal thing here. Okay. Long process. What we tend to do, let's go with it here. So we do have statistical software. Don't need to write this down. They do all this stuff for us, right? So we're kind of doing the nuts and bolts in an introductory statistics class. The industry standards usually are something called Minitab and StatCrunch. Those are kind of like the two. For small companies that can't or don't want to buy these programs, what tends to happen is they'll use Excel, Microsoft Excel. They have all those things too. Just needs to require a little bit more, but thoughtfulness how you want to plan it out. But really, it does that. I will say the district researcher here in the district, what he does, he uses Excel all the time. He has everything in Excel. And so you ask him to put some data together, like, yeah, sure. And it spits it out in Excel. There's also another one that just came on the scene, a cloud service. It's called Tableau. And Tableau is what the college accepted about 2 years ago, bought a site license. And pretty much the researcher can go in it. It has all the data inside there. I mean, everything that you can imagine. And click of a button, click, 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 click. You know, I want the average GPA of students. I want the average GPA of the students in this program. I want the number of students that enter college as a cohort and how many students graduate 2 years later or 3 years later as a cohort. And so all the data is available. In fact, the reason why you guys are in a statistics class right away after high school, because you did not know this, because 5 years ago, you would come into college and you'd either go into Algebra 1 or Algebra 2 or statistics. And so the state of California decided about 2 years ago, saying what we're going to do is we're going to get rid of the algebra classes as 2 separate classes. All students are going to be funneled into a statistics class or a pre-calculus class as much as possible. Unless they really, really don't want to, then they're going to go back to an algebra class. And that algebra class is going to be a combination of Algebra 1 and Algebra 2. Okay, why am I telling you this? Is because they ran a lot of statistics and they said, look, this will be the better model for students to exit out of college. That's it. So there's a whole uproot in the math department and English as well, because they played around with a lot of statistical data. Like, hey, look, we're going to get 3 times the number of graduates if we do it this way than if we do it the old way. We're going to implement this as law. So there was called Assembly Bill 705. It was passed, and then everything changed. College changed after that. So kind of interesting. Anyways, there's that. Let's go with one. And this is kind of like the spit out right here. This is a number of hours. If we were to do it in Minitab, this is what we do. N is equal to 40. Here's your mean, standard deviation, and then it spits out the confidence interval here. StatCrunch does the same. Okay, one example. Let's go with it here. Right here. Can you guys go all the way? So college admissions director wishes to estimate the average age of all students that are currently enrolled in the college. Apparently, they did not feed that into the machine. They did not put the birth date into a machine for some reason. So in a random sample of 20 students, the mean average is found to be 22.9. Also from past studies, they've done this before. And it seems like the standard deviation is right about 1.5 years always. The mean sometimes changes, but the standard deviation remains to be pretty good. The thing is, since we only have 20 students, we have to make sure that the population is normally distributed for us to do this. So it is. Okay, all yours here. Can you construct a 90% confidence interval on the mean age, the average age of the college students? because the admissions director asks to. Okay, give you guys a little bit of time. Try it yourself before I reveal the answer. So I want to do exactly what we did before here. Gives you a little bit of time. I'll give you guys answers slowly. All right, let's go with it here. So I gave you guys a little bit of time here. So let's see if you guys have the same numbers I do. So is n equal to 20? Is that right? Our X bar is 22.9. Standard deviation is 1.5. And our confidence interval at 90% is 1.6, or z-score at 90% is 1.645. Good. And now let's look at the tabulation data. Here it is. A margin of error for 90% confidence interval is 1.645 times 1.5 over square root of 20. Now, the reason why can we use 20 is because it said it was normally distributed, right? So age is normally distributed. Yeah, it could be. If it was 20 and we just kind of left that, like, hey, just 20, then you would say, can't use this. It's not equal or greater than 30. We're good. You have to have at least 30 in your sample, unless you know it's normally distributed. So 0.6, we got that. And all we do is we subtract to get the left-hand side. So 22.9 minus 0.6, we got 22.3. Right-hand side, we get a 23.5. Voila, and we got this. And then can you graph a little graph based upon that? And the kind of like the fast way of doing it is you just put in those 3 dots. So put in your 22.9, put that on a graph, extend out to the left-hand side, put a 22.3, extend to the right-hand side, 23.5, and done. All right, we're good there. People are on their graph now already, so that's cool. Let me show the graph here just as you guys finish up. Tell me if you need to go back to the slide here, but here's my little graph. And so the quick, sort of like the quick dirty way of doing the graph here is you put your dot for your point estimate of 22.9. You put your, and make these lines kind of like the same away from each other, and just put in the 22.3 where it's that at, and 23.5 where that is at, and that's it. Okay, so what is this saying? That's the question. What is this saying? And so we're running confidence intervals. As we do hypothesis testing, chapter 7 and chapter 8, the whole goal of chapter 7 and chapter 8 is to have our sample, and we reflect upon what's happening in the population from the sample. That's the questions, chapter 7 and 8. We're good? For confidence intervals, this is what we're trying to think about. We're trying to think about this right here. We're trying to say, as I jump to the next slide here, we have 90% confidence, right? So if I do this here, if I was to take other samples, I ask another 20 students, we good the next day, and ask another 20 students the next day, another 20 students the next day, right? Each time I keep on asking those, I have 90% confidence that at the same sample size, I keep on doing this. And normally I'll get 9 out of 10 that always fall in this mu value. Are we good? So I got one, of course, it's mixed data here. So I got one time I asked the students, there was 20 of them, and the mean average age was actually less than with the confidence that I have. We good? So it's how much confidence do I have in 20 people asked again that the sample interval will fall, or that the average will fall back in line into there. We're good. That's kind of what I'm asking for. Okay, one more thing to cover. I think, yeah, one more thing to cover in 6.1 is this right here. Is given a confidence interval and also the margin of error. The question is, what's the smallest sample size that's needed in order to estimate the mean? I was in a meeting the other day and we talked about getting information from the community. That was the question. How do we get information from community? And so there was a survey that was done. We were looking at a survey. Let's see, what's the specifics of it here? Oh yeah, so we didn't get that much of a response from the survey. And so then the question became, okay, so how do we do this better? So it was a whole county as well, trying to include the whole county. And so the researchers there, obviously. And so we're looking at the sample data. And then so one person says, look, can we do, I want to be able to spot every single one, right? Every single one of these counties or the small areas, right? Because we have many towns, small towns, right? And so we're going to do, we got results from an online survey. There we go. We got results from an online survey, and the person in charge said, well, that's not good enough. I want more than that. And so we started brainstorming, and one of them says, okay, let's just hire out a person that would actually randomly select cities, right? And people in those cities, and start going door to door and asking, things, asking questions. And so the researcher says, yeah, that's great, but it's going to cost you $20,000 per week to do so. And then that's just the front cost, right? And so it was interesting because you got this like, hey, this is the survey. We don't like the results. Here's what we can do. And then like, that's going to cost way too much. Okay, now the question is, how do you sort of get in the middle, right, of it? So then it becomes, okay, let's talk about the cities where there's the most amount of impact. Okay, it's these cities right here. Okay, how about if we just do for those cities, at least we'll get a sense of what's happening, right? And then we can extrapolate that to here. So for vocational programs, but it's one of those, there it is, there's your cost. So the question is, what's the minimum size needed in order to estimate a certain population mean? There it is. So here it is. If n is not a whole number, then we round up. Okay, we round up to the next whole number. Don't round down. And if the standard deviation is unknown, you can estimate it by using little s. You guys tell me, what is little s? What is little s right here? Dun, 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 dun. So if n is not a whole number, what we do is we round up always. If the standard deviation is unknown, you can estimate it by using S, provided you have a preliminary sample with at least 30 members. I don't know, I was writing stuff down here. So let's go back to our estimate for our student athletes here. So since we're doing that example here. So since we've done the preliminary work on it, So researcher, example one, of course, here it is. Wants to estimate the mean number of hours spent on required athletic activities by all student athletes in the conference. How many student athletes must be included in a sample to be 95% confident that the sample mean is within 0.5 hour population? So I want it to be super close. I can say about this many hours, really. So you guys talk to me here. First things first. Our confidence is 95%. Tell me the z-score. Tell me z-score we want. Go for it. Yeah, negative 1.96, positive 1.96. So we normally just use the positive value since it takes care of both the positive and negative. Okay, and then we need the standard deviation for this guy. If we not, then we have to calculate standard deviation of our data, but we don't have time for that here. So I'm going to say standard deviation is 2.3 from example 2. Okay, and try this on your calculator here, just real quick here. E is 0.5. We just want a half an hour difference. And so try it, see if you guys get the same number here. So it's 1.96 on top times 2.3, which is standard deviation, divided by 0.5. And all that you're going to square. So again, I'm going to walk around just to make sure you guys get the 81.29 real quick here, and then we'll keep on going. Okay, since it is not a whole number, we have ourselves 81.29. So we're going to bump it up to 82. Oh, not fun. How many athletes did we have in the beginning of it all? Say again? 40, huh? So, okay, so in order to bring this down to a margin of error of a half an hour each way, we're going to have to add 42 more athletes, right? And then also note, this is just the bare minimum, right? To get this computationally here, this is bare minimum. So we're going to have to need 82 samples to get this within a half an hour pair. Okay, are we good there? Okay, I'm going to pause just for a second. Okay, I prefer to do 6.2 at the same time I do 6.1 because it's the same stuff. We're thinking about the same things. Only difference is we're going to make confidence intervals. The only thing is standard deviation is unknown. That's it. That's the only difference between the two. And so question is, how do I make a confidence interval if I don't know? The standard deviation. Okay, so let's go with it here. About 18 slides-ish. We should be done with that one here. So first things first is because we do not know the standard deviation, this is it. We have ourselves something called a T distribution. So when the population standard deviation is unknown, we also can do it when the sample size is less than 30. So we can only get 10 people to do the survey. We do have to have at least some kind of confidence that our data is somewhat normal distributed, you know, like age, right? Or something like that. So they have some kind of normal distribution. So here's it is our variable is T, and big equation, but we'll master it in just a little bit here, guys. So we say the average that we get for our sample, subtract the average of the population, And then we have ourselves this crazy thing. We have ourselves standard deviation of our sample divided by square root of n. So this little extra standard deviation piece is there. Okay, good there. I already wrote that down at least. Okay, let's jam with it here. So I will print these slides out just so you don't have to write down all of this, okay? But let's just kind of at least read through them here. Oh, got a few people still writing it down. Go for it. So we have ourselves, we can't use the normal distribution because that's based upon z-scores, right? It's based upon a normal distribution. A standard deviation is known from the population itself. So what a t distribution is like, it's kind of like putting in like slow amount of z-scores and putting in slow and thinking about what's the shape of the graph going to look like as I get more and more values inside there. That's kind of it. So it's almost like taking something normally distributed and saying to ourselves, hey, what is this going to look like if I just had less sample sizes? That's kind of what I'm looking at. Okay, so let me do that here. Let's read through this just real quickly here. So these are the conditions that are placed upon. So the median, mean, and mode of the t distribution are equal to 0. So the middle is the middle. We're good. It means it's equally distributed on both sides and it's symmetric. We're good. That's kind of, we'll see this graph. It's going to look just like a normal distribution, right? So don't need to write these down. Just kind of think with me. I'll post these slides up here. It has to be bell-shaped and symmetric. The total area still is going to be 1, just like a normal distribution. And then the only thing that happens here besides a normal distribution is that our ends are going to become thicker. So it's a thicker ends and the top of it is a little smaller to compensate for less samples. Okay, and then we know standard deviation of t is going to vary with the sample size itself. Okay, so what we do is we think about this right here. You guys talk to me. How did we adjust for air and samples? Do you guys remember how in chapter 2? We adjusted for our air whenever we was like, oh, you know what? This is a sample distribution. What am I going to do to adjust for that little air in samples? Anybody thinks back all the way to chapter 2? It's been a long time. I think we did this. Instead of dividing by n, what we did is we looked at n minus 1. And so we kind of took the number of samples, we subtract 1 from it to give us that divider. So our divisor is a little bit bigger. So what we do here is we call this degrees of freedom. So degrees of freedom is the number of free choices left after the sample statistic is calculated. And so DF is usually the designation for it. And so when you use a t distribution, you estimate the population mean. The degrees of freedom are equal to just 1 less than the numbers we have. So that allows us almost like this extra little give to our data. Okay, so here's kind of just a quick little view of it. This is kind of what it looks like here. So if the degrees of freedom is 2, notice the shape a lot more thicker at the ends. It doesn't come up as high and it goes down because it just allows more area on the bottom to go in each direction. That's all this means. As degrees of freedom equal 5, notice it's shaping more and more like the normal curve, and that blue one right here is just the normal curve. And so it's almost like, we call it t distribution, but it's thicker at the ends at first, and it gets shaped more and more and more closer to that, depending on how much sample sizes we have. Okay, so let's jam with with this right here. So let's do the table first. Let's see what time we got. Yep. So here it is. Find the critical value for a 95% confidence when the sample size is just 15. So now to notice, it doesn't say it's normally distributed, right? It just says, look, I got 15 people I asked. What's their age in college? That's what I did. And so by table, here's what we're going to do. We've got to get our textbook. We're going to go find the T distribution in our textbook. So it's going to be table 5. It looks like this. So it's the first flap cover I think you get to as you open up the back flaps. And I'll show a picture on it down here in just a bit here, but I want you guys to at least try it to find it on in your book as well. So we've got the front book cover. You guys, talk to me here. Everybody found table 5? It just says T distribution. We're going to look at degrees of freedom here. So sample size is 15. What are we going to look at? What chart number are we going to look at? Actually, no, let's go across the top here first. Notice the top. It has, let me read it from upside down here. So level of confidence, I got 80%, 90%, 95%, 98%, and 99%. So I want column number 3. Is that good? Looking down. Well, let's see, since the N number is 15, I'm going to go 1 less. So my degrees of freedom is what determines that going down. So I'm going to go to 14. Those of you that don't have a book, this is kind of what it looks like here. So notice the 80%, 90%, 95. I want the 95%. And I'm looking down and I'm going to go to 14 because it allows me that extra little space. So 2.145, give me a thumbs up if you found 2.145 that you had a textbook with and you looked it up. Thumbs down if you didn't find it or having trouble finding it. Okay, we're good there. Okay, that's by chart. So that's by chart and T distributions. I think even nowadays people use T distributions by chart. Just a lot easier. They're set and sound here. And so what we're really trying to do is do this right here. Let me give you the visual illustration of it. It looks like this. 95% confidence. If I was to make a normal distribution only with 15 units or 15 samples, that's what it usually looks like. And this is about doing a whole bunch of samples of 15. We're good? That's kind of what this is from. So it gives you a little bit more leniency at the ends. Gives you a little bit more leniency. So remember for 95, what's the Z-score for 95%? Yeah, 1.96, huh? So then 1.96 is a lot more, notice it's a lot more like right here, huh? Right? So the T-score allows you to kind of spread out that value there. Okay. If we do it by calculator, let's go by calculator here. So we need to find the Z-score by calculator. And so what we do is we punch this area in here. And so let's go back to our chart because this will sort of help here. I'm trying to find a Z-score, a T-score of this. Now, just like the calculator, it doesn't, it's dumb. So when you enter a data for it, it's only going to give you, it gives you all of this right here, all to the left. So it's going to actually include all this area as well. And so what we want to do is we want to include this little piece right here and that little piece to give us that little end cap. Okay. So find that. So we include the 95 plus that. So we're going to look for a 0.975. Okay. So those of you with a TI 84 plus calculator, you guys should still be able to do this here. You're still going to go under the distribution, right? Menu, and you should find a inverse of T. I do not have it on mine. Mine's a TI-83. That's no fun. So try that on the graph there. Okay, and you guys talk to me. Did you guys thumbs up if you got 2.144786881? Raise your hand if you need help. Okay, real quick here. Sorry. Thumbs up if you found it. Let's do that here. Thumbs up. Thumbs down if you need help that you did not find it. Thumbs up now. Okay, cool. Okay, I'll come by as well if need be. Okay, let's try a solution. I think we'll be done at that point. Okay, boom, example, and we're good to go. Here's our example. Yeah, coffee's good here. We select 16 coffee shops and measure the temperature of the coffee sold at each place. The sample mean temperature is 162 degrees Fahrenheit. Sample distribution is a 10 degrees Fahrenheit. Can you guys give me 95% confidence interval for the population mean? And let's do this one together as I'm kind of looking through it here. Okay, see if this makes sense here. So n is equal to 16. X bar is 162.0. The little s is 10. C value is 95. Since there were 16 shops that was given, that means degrees of freedom is 15. And let's use table 5 to find, or a calculator, to find the t value. Okay, so what we have to compute is margin of error, right? We want to see how much error we get from the mean, because we already have the mean. Mean is 162. So now to give us, we already have the point estimate, as the book calls it. So we got to calculate this guy, margin of error. So real quick, before I get there here, you guys talk to me here, using table 5, however you feel comfortable, or using a calculator. Can you guys get to 2.131? Calculator or by table? Go for it. So using degrees of freedom is 15 and using 95% as your confidence interval. All right, again, thumbs up if when you got it, or thumbs down, you need help. Cool, got 1, 2. All right, thumbs up if you got 2.131. Thumbs down if you need help finding the 2.131. Anybody with the help? Okay, good. Then we've got to find the margin of error, of course, at 95%. Since I know my t value, 2.131, I plug it into the standard deviation of 10 divided by the square root of 16. All right, 5.3 is good. Tell me when you get 5.3. I'll ask for thumbs up or thumbs down. All right, and let's go with thumbs up if you got to 5.3. Okay, and thumbs down if you need some help. Okay, and now I think I got what I need because the next point is just to add and subtract to my average. So I need 162 minus 5.3, 162 plus 5.3, and with good confidence, there's what I have. Man, things escapes me here, but I think it was like in the 1990s, I believe. There was a lady that went through the drive-through at McDonald's, and she picked up coffee early morning, and then she drove off, and she hit her brakes, and the coffee spilled on her. And even through clothes, it actually did physical damage to her. Burned her skin to the point that she did need to go to the hospital for it. So then she sued McDonald's for a lot of money. And the question was, in the court case, and people had so much opinion. It was like everybody had an opinion about that case, like, oh, whatever. She's just suing a company for just to get some money, right? And then the other opinion was like, yeah, no, we should have really set standards for restaurants and how hot the coffee should be, right? So then the court case came about, and to the point that restaurants do actually have a standard of how hot the coffee should be. And McDonald's, what they do is at least I'm sure if they changed by now, but they serve the coffee extra hot as it came in from the coffee maker. And what they had to do is they had to push it off to the side, and they had to be there for, I think, 3 or 4 minutes for it to cool down to the appropriate temperature. And then the customer gets the coffee. That was the way it was made. And that's the way the process worked. And so what they did is employees did not do that. They didn't wait the 3 minutes that you're supposed to. So they just, from the tap, right? You close it up, you give it to the customer only. That was it. And so she won. I think they even awarded her more money because they were grossly error. So what happened was one of the evidence that they actually had to do is they go in and they actually inspect the temperature of the coffee. That's exactly, I think, maybe why this example is in there, as a reminder of that right there. It's right about that time. Or at least it's in memory, really, of people. I'm sure the author, as he writes the textbook. Okay, so we're good there. So it looks like this. If you want to give me a confidence interval, 162 right over here. And again, don't need to do the numbers on the bottom, but you for sure need to give me the top 3 numbers there. So confidence would be from 156.7 to 167.3. If memory serves me correctly, I think skin actually starts like damage at 180 degrees. That's when you're like, whoa, that's too hot. Skin can't handle that. Okay, almost there, guys, and we'll go early here. One more example. We're not going to crunch the numbers on it. I just want to show it to you. We're good. Those watching the video, you do have to crunch the numbers. Okay, so let's go with it. Brandon was selecting 36 cars of the same model that were sold at a car dealership and determine the number of days each car sat on the dealership lot before it was sold. Again, this is huge. This is exactly what they do in industry. This is exactly what they do with house sales as well. Same thing here. House sales go by the same rules there. They'll look at how much time someone sits on the market. Sample mean is 9.75 days with the sample deviation of 2.39. That's cool. Construct a 99% confidence interval. That's cool. And so if I were to do that, because standard deviation is unknown, the sample is random, and n is equal to 36. We're going to still use the t-distribution, agreed or disagreed. And it's because the standard deviation was unknown. That's the problem. Using the t-distribution, n is equal to 36. There's our average. There's our standard deviations of the sample, confidence interval. That means the DF has to be 35. We're good, degrees of freedom. And can you guys quickly find, either by table or by calculator, can you find for me the 2.724? At least that's what we'll do. And we'll run through the rest of the example. All right, again, thumbs up, and just I'll call for thumbs up in a little bit here, but your job is to find the 2724, not the whole problem here, just this little piece right here. Find me by calculator or by table. Okay, what you need for it is you need this thing for it, right? And the n number. Actually, no, the degrees of freedom would be better. Degrees of freedom and the confidence interval. There's what you need. So on a table, you're looking at the 0.99 confidence and degree, and go down to 35 for degrees of freedom. Or on your calculator, inverse of your t distribution. Just make sure you're looking at, was it table 5, right? Yeah, table 5. Okay. Quick show thumbs up if you found it. Boom, 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 boom. Got 2 more people, or at least waiting for 2 more people. Cool. Good, good. Awesome. Okay, thumbs down if you need some help. Okay. No problem. Okay, and then let's see. No problem. Guys, what did you guys come in for your area? 0. Let's see, 0.995. Is that right? That's the good area. And you try to put 0.995. And go down, and that would be 35. Okay, cool. We mentioned that here. The class real quick here is good. I'm glad that someone asked for help here, because I do have to mention it. On your calculator, if you do it by table, table's good, right? I see people did it with by table, they had their thumbs up real fast. People that did it by calculator, you had to do what? You had to do this right here, right? And then you had to think about t distribution. There's my 99% is right here, right? But I have to get this, and I have to include this little piece right here. So I'm thinking to myself, that's 99. That means I still need 0.5% here. And I still need 0.5% here. True, true. So when I do this here, this is 0.99. This guy changed to decimals would be that right there. I got to add these guys together. So as you punch in the calculator, you should punch in 0.995. And then your DF would be, so those are the 2 numbers you need for the calculator. That's the only tricky thing with the calculator, not doing my table. Okay, and then we jump to it. If that's the case, 1.09, subtract from the mean, add to the mean, and you get yourself that right there. Again, don't need to write it down right now, because we're kind of just going through it fast. There's your confidence interval at 99%. Okay. So 6.1 and 6.2, we just learned these confidence intervals, and we're trying to do it for the mean, right? And so question comes up always. Oh, I guess I should mention this. So StatCrunch, it does it all together as well. If we need to do that, you'll put in things there as well. But here's what I'm thinking, the logic process used. Here it is. This is kind of what we kind of think about here. So am I doing a normal distribution? Am I doing a t distribution? So is the population normally distributed, or do I have more than 30 people in my sample? That's the question. If it's a yes, if it's a no, let's do no here. You cannot use the standard deviation or the t-distribution. You're just stuck. We're good. If it's a yes, if the standard deviation from the population is known, we use the z-score. If not, we use the t-score. We're good? Or the t-distribution. At that point, we're good to go. Same formulas are the same. Okay, with that, we could do one more example. How about this one? Just to say yes or no here. Let's see, you randomly select 25 newly constructed homes. Sample mean construction cost is $180,000. The population standard deviation is $28,000. Talk to me. Is it a normal distribution, a t-distribution, or neither? Someone said normal. How come? Yeah, we're looking at, so because we have 25, we go back to our list. So it's less than 30. Uh-oh, we might be going this direction. We're good. Then we still keep on looking. We're like, oh no, look at this. Costs, construction costs are normally distributed. Okay, phew. That's cool. That allows me, that's true. So we go down to here. Then the next question is, do I know the standard deviation of the population? Yes, I do, right here. It's 28 grand. That's cool. Oh, going backwards here. So therefore, I go to this right here. I'm going to use a standard normal distribution. Where have I seen this before? I was repairing my heater at home, and the diagram is exactly like that. Is called schematics. And whenever you do schematics of yes and no, if you do troubleshooting on a computer, on a heater, on an air conditioning system in a car, electrical system in a car, this is all just like this. It's this whole schemata of yes and no, this is the problem. Yes, 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 no, this is the problem. And then you go fixing it here. So true. So we got that. It is yes, it is. Population is normally distributed. Yes, therefore we're going to use a standard normal distribution to figure this out. Okay, with that, we are done for the day.